In our last episode, we looked at bubble sort, which works by slowly pushing the largest numbers out to the edge of a list. But today's algorithm takes the exact opposite approach. Instead of pushing, it pulls new values in, sliding them right into place. This diagram shows where algorithm number 2 sits among the 50 we are covering. It's called Insertion Sort, and it is located right here in the sorting category. If you've ever held a hand of playing cards, you already know how to execute it. You keep a sorted hand in your left hand. When you draw a new card with your right, you don't resort the entire deck. You simply scan your current cards from right to left and tuck the new arrival into its exact slot. Because this sounds like a beginner-level concept, you might assume the software running your phone or your bank has moved past something so physical and rudimentary. This diagram reveals the secret inside the world's fastest sorting systems. Sort, standard in Python and Java, chops datasets into tiny runs because insertion sort is mathematically unbeatable here. Below, C++ intro sort drops below a 16-element partition and falls back to insertion sort. Understanding this physical card sorting motion matters because it is the actual computational engine doing the close quarters work in the hybrid systems we use every day. To see how it handles that work, we have to look at its primary rule. The algorithm must establish and maintain a completely sorted prefix on the left side of the data. This visual shows the process on an unsorted list. The algorithm treats the first number as a sorted prefix. As the next keys are processed, they're pulled into place, expanding the violet cells, until the 1 sinks to the front. The mechanical advantage here is isolation. The algorithm securely grows that sorted prefix by exactly 1 element per pass, remaining entirely blind to the chaos of the unsorted numbers waiting on the right. If we zoom in on a single pass, we can see exactly how it moves data to create that perfect isolation. This image details the inner loop. While bubble sort swaps adjacent elements, insertion sort simply shifts larger elements to the right, opening a temporary gap. As step 3 shows, the final action drops the active key into that newly created gap. A traditional swap takes 3 separate steps to move a single variable. By shifting everything over and doing a single drop, this algorithm heavily reduces its computational overhead, which is exactly why it dominates on small datasets. This chart shows 2 diverging trajectories when we look at time complexity: a flat linear path for its optimal performance, and a steep quadratic curve for its total failure state. In a best-case scenario, where the data is already nearly sorted, it operates in linear O of n time. The algorithm only has to make a single check per element, requiring 0 shifts. We see this logic in the code itself. The highlighted line is the inner loop controlling the shifting mechanism. By using a strictly greater than symbol instead of greater than or equal to, the code stops shifting at a matching value, inherently keeping the sort stable. But this localized checking is also its absolute limit. If you feed it a massive, randomly ordered dataset, every new item forces the system to scan and shift thousands of elements, triggering a quadratic collapse. That is when you need a tool like merge sort. So its ideal deployment zones are highly specific. It thrives on streaming incoming data, it cleans up nearly ordered lists, and drives modern hybrid sorts. If you want to dive deeper into the code implementing these algorithmic strategies, check out this book, 50 Algorithms Every Programmer Should Know. Insertion Sort proves that the most advanced digital systems we rely on are often built on the most basic human instincts. Up next, we look at Selection Sort, an algorithm that abandons the idea of tucking data in and instead hunts the entire list for the absolute largest value.